Hi everybody, it's Mrs. Peachy from your WCA physics class, and I'm going to be doing this video tutorial on your current and resistance laboratory, which is Unit 2, Lesson 8 of second semester physics. So this is two of three portfolios for this semester. Okay, so let's see here. Before we begin with the actual kind of tutorial here, I just want to remind you that on my website there is a link to the lab rubric. Please make sure you look at this if you have not done so far. I do have quite a few of you that are still submitting portfolios that are not done completely and are losing quite a few points because of that. So make sure you are looking at and following the lab rubric, okay? So for this portfolio, you are going to be using a simulator to look at what happens in a circuit. What happens in a circuit when you alter the resistance or the voltage of the circuit? What happens to the current? And remember that current is the rate of the flow of electrons through the circuit itself, right? So it is measured in coulombs per second, which is the flow of charge, whereas a coulomb is roughly equal to, don't remember. I always forget this one. It is equal to 6.24 times 10 to the 18 electrons. Yeah, that's a big number. So that's why we use coulomb instead of electrons there, right? Although when we do look at the picture, the simulation shows electrons, it's obviously a representation of what's happening and not exactly what's happening, because the size would be completely wrong. So before you begin this, the first thing you're always going to need to do is to do a hypothetical portfolio design. So what this is asking you to do is to think about how could you do a similar type experiment hands-on at your house, or if you had access to a physics lab or something like that. What materials would you use? What steps would you take? What data would you record? And if the results didn't work out like you expected, why might that be? And so that last one really is something that stumps many of you. And what I want you to think about are potential sources of error. Things like errors in calculation. Potentially you may have external variables that you didn't account for. Maybe your setup was done incorrectly. Maybe you have malfunctioning equipment. Maybe you just didn't understand the concept very well, and so you hypothesized incorrectly. Think if there's anything else that you might include in there. I think that's probably about it. You may think of other things that may be sources of error, but please do not say human error, because that's way too vague, and I want to know what errors the human may have made. And obviously it's not robot error, right? So, let's look at the lab then that you will be completing. You will need to develop a hypothesis. What do you think is going to happen? And why do you think it's going to happen? Remember to use your textbook to cite some sort of evidence that supports your hypothesis. That's necessary for full points in this section. You're going to answer the questions. How will changing the voltage change the current? How will changing the resistance change the current? And yes, Ohm's law is a very good indicator of what might happen. But then you also might want to explain conceptually why Ohm's law is something that makes sense. Okay, then it's going to take you to this sim, which is one of the PhET sims, which I do have up and running here. And I'm going to quickly pause this because I want to give you a little bit of information about this. One thing to notice about the sim is that if you stop the circuit, so you would disconnect the wire or you would open up the switch or whatever, the electrons stay put. They don't go anywhere. They stay where they are. So you're stopping essentially you're taking away the energy, the potential energy or the difference between the two poles of the battery. So you're basically stopping everything in its tracks at that point. So when you resume it, when you connect that circuit again, the electrons continue to move. There's no pause in the action. So think of it this way. The battery provides a potential difference from one end of the battery to the other. You can it's kind of analogous to a ramp providing a slope that will allow a ball to roll down it, right? If I stop it for a moment, if I shut the switch, it's kind of like just removing that potential difference. But the ball, because I'm too shaky, won't stay where it's supposed to. In theory, the ball will just stay where it is, right? It's not going to go anywhere. It's not going to just go and go back into wherever it was before. It's still going to stay there. And when you turn the switch, shut the switch or connect the battery again, it again will start to flow. Now, if instead of having one ball, I have a whole bunch of them lined up end to end to end to end, what will happen when I resume, connect that battery back up, is that the balls will continue to roll and one ball rolls into the other. So when the first ball rolls, when the first ball rolls, the last ball will roll simultaneously, right? And so even though the electrons themselves don't flow super fast, they actually flow at a rate of about 10 millimeters a second, which is a centimeter a second, so about this much in a second. Because they're all lined up, the whole thing is kind of moving all at once. So when you close that switch, that power is turned on instantaneously, even though the electrons themselves are not moving instantaneously. Interesting. So I want you to think about that a little bit. And now you're going to also take some data. So you're going to have some columns that are set up. You're going to have trials. You're going to have to set up the resistance, the voltage, and the measured amperage. You're going to look at the relative speed of the electrons as well as the temperature of the circuit here. Okay, right here. So speed, slow, medium, fast. Temperature, hot, medium, well, cold, medium, hot, whatever. Amperage, we're going to have to estimate using the ammeter. You're measuring it, right? But the ammeter is not super precise. Every line is 10 amps. So you have to kind of mentally divide each of those little spaces into 10 spaces to be able to get it to the nearest amp. So you should only ever give me here to the nearest 1 amp, right? You can't go any more precise than that using this particular instrument. So let's kind of look at this. Notice the electrons are flowing out of the negative end and into the positive end. This is actual electron flow, not conventional current. Now, I'm not sure if we can accurately determine the relative speed here without seeing a bunch of them. So you may have to, increase the voltage a little bit to kind of see, how does this compare? Just to kind of give yourself a bit of an idea, Oh, my battery turned around. Oh, I was at negative. There we go. Here we go. That's where I started off anyways. So you'll kind of record the relative speed. Notice that it's vibrating these atoms that are in the resistor, right? So think about how vibration of atoms is a measure of temperature, right? Because temperature measures average kinetic speed, or the average amount of kinetic energy of the atoms that are in motion. So when you have an increase in temperature, you should have more kinetic energy, right? They should be moving faster. And if they have more kinetic energy, in theory, the temperature should change too, right? because that's what it is. That's what temperature is. It's a measure of the average amount of kinetic energy. So if those things were moving faster, what might you think would happen with the temperature? How would the temperature correspond to that, right? I'm not going to answer that question. I want you to kind of figure that one out for yourself. So now I look here at the amperage, and I'm going to estimate it's about 8. About 8 amps, okay? Which is fine. It's a pretty good estimate, actually. So then I'm going to go to my lab here and see what questions it wants me to answer. So it's going to ask me to do some calculations. In addition to the data that I recorded, you're going to use Ohm's law to calculate the actual current, the actual amperage. I estimated 8 using my ammeter. Let's look at what the calculated value would be. Voltage divided by resistance. Well, the voltage is 2.88 and the resistance is 0.4 ohms. 7.2 is my calculated amperage. Okay, pretty close, right? Not bad. I mean, maybe if I had measured 7 or estimated 7, you could really give me a standing ovation, but I don't think that's terrible. So now let's calculate the absolute, or the relative error, okay? Relative error. Well, there's the absolute error, which tells me how many amps I'm off, and I'm off about 0.8 amps, right? So that's my absolute error. But I like the relative error better. It's giving me a percentage. How close am I? So I'm going to take the estimated, which was 8, subtract the 7.2, and divide it by 7.2. And that gives me 0.111111. Okay? So it tells me I'm approximately 11% off of the actual value. I don't think that's that bad. 91% right, 11% wrong, right? Or wrong, I don't know. All right, so you also then need to do a graph here. So you're going to be graphing on the x-axis, you put voltage. On the y-axis, you are putting current. So voltage and current. So Y, current, divided by voltage. Current divided by voltage would be resistance. So this, when you calculate the slope of this line, you're going to be able to get, or you should get, the resistance, right? Because this is a fun 3-variable formula. Finally, you are going to be doing some analysis questions. Don't forget, please type the question up and then write the answer below in a different color. That helps me tremendously. And then always, when you're referring back to some conclusions, use your textbook as reference and cite it within the conclusion, because that just gives a lot more support to what your conclusions are. All right, everybody, that is it. If you have questions or concerns, feel free to give me a call at extension 2204, or you can send me a webmail message. Have a great day, and happy St. Patrick's Day.